Welcome back, everybody. I want to start off today by going over one of the homework problems that was assigned last night. I'm not sure how well you guys did on that, but I think it would be good for us to go over one of those. So I think the homework problem that I'm going to go over from Momentum 2 is number 5. Number 5 seems to be a pretty good problem as far as what an explosion looks like. So here we go.
Okay, so number 5 on Momentum 2 is an explosion problem. The problem basically talks about a rifle that is firing a projectile, and that firing process constitutes an explosion. When you look at this problem, you can see that both the bullet and the rifle were at rest at first, which means that the initial momentum of the system is 0. The law of conservation of momentum then basically just says that total momentum is the same afterwards too. So knowing that the total momentum afterwards is 0, and knowing that total momentum will be due to the momentum of the rifle and the momentum of the bullet, I basically start off by first of all finding the momentum of the bullet by taking the mass of the bullet times the velocity of the bullet. I come up with 4 Newton seconds. Well then, since the total momentum is 0, and that's due to the momentum of the rifle plus the momentum of the bullet, I can make this statement right here that says that the momentum of the rifle is really the same as the negative momentum of the bullet. That way they could add together to be 0. Therefore, the momentum of the rifle must be negative 4 Newton seconds. And simply then, I go and set the momentum of the rifle equal to negative 4 Newton seconds, solve for the velocity of the rifle afterwards, and I come up with 2.2 meters per second. Notice that I do get a negative sign in my answer. That's a pretty crucial thing. The negative sign tells me that the rifle goes in the opposite direction that the bullet did. Since I made the bullet's direction positive, that would mean that the rifle's direction would therefore be negative. Also, the speed of the rifle makes sense because, you know, a bullet goes pretty fast, 400 meters per second. The rifle does kick back with some speed. It's hard to see that because a person's arm would be, or a person's shoulder would be steadying that. But if you actually allowed the rifle to fly backwards somehow, you would see that it moves at about 2.2 meters per second in this example.
So we've looked at explosions where two things blow away from each other. Now what we're going to do is turn our eyes towards the type of interaction where objects actually bounce off of each other. So we'll be looking at collisions. The type of collisions we'll be looking at might be like this, where one object bounces into another object and then they literally bounce off of each other. What's going to happen there is going to depend on the masses of the vehicles and what their initial momentums were in the beginning. So there's lots of different scenarios that could make this happen. Okay? This is one of those things you could play with all day long, frankly. Okay? The other type of interaction we're going to look at is when objects hit and stick together. Okay? When objects hit and stick together, this is called an inelastic collision. So an inelastic collision might look something like this. Okay? Still, in both of these things that I'm showing you, the law of conservation of momentum holds true.
All right, so let's talk about inelastic collisions first. An inelastic collision is the kind of collision where when things hit, they actually stick together after the collision. This was the case that I showed you with the 2 carts up front. There's some Velcro tabs on those carts that allow those carts to stick when they hit together. This could also be the case of, I don't know, many car accidents where you see one car hit another car and they stick together and slide together after the collision. Another case of this would simply be if I fired a bullet into a stationary block of wood. The bullet will essentially stick in the block of wood and they'll move together. In all of those scenarios, the law of conservation of momentum holds true. Remember, the law of conservation of momentum simply says that the total momentum in a system is the same before an interaction as it is after an interaction. So in this case, when I talk about an inelastic collision, the interaction is that they hit and stick together. A way of writing the law of conservation of momentum here would be like so, where I basically say that the total momentum of object A, I'm sorry, the momentum of object A plus the momentum of object B would equal the total momentum in the system. That would be equal to the total momentum of both of them stuck together afterwards. So in this statement right here, I say the momentum of object A plus the momentum of object B. Those basically equal the total momentum in the system. That equals the momentum of object A and B stuck together after the collision, which is still the total momentum in the system. Down here below, I just basically drew it out a little bit more algebraically so that if you're good at algebra, you could just solve for one of the variables. But I really would want to show you how to do this in a little bit more of a thoughtful problem-solving sense so that you can apply what you've learned here to lots of different situations. So let's go ahead and do an example that shows how to do a problem like this. The example that we're looking at says this: a man is driving his 2,200 kilogram Ford F-150, including his math, southbound on C-470 at 8.2 meters per second in heavy traffic. An inattentive driver of a 1,400 kilogram Honda Civic, again, including the driver's mass, slams into his truck from behind. The two cars skid together after the crash. From the skid marks, the sheriff investigating the crash figures out that the car and the truck were moving at a speed of 15.9 meters per second just after the crash. How fast must the Honda have been moving just before the crash? All right, so look, guys, in this problem, there is a lot going on. I think it's a good idea for you to take a moment to just try to interpret this problem to see if you understand what's going on. So I would just say the F-150 is moving and rear-ended by the Civic. They hit and stick afterwards. Right? This problem shows or talks about an inelastic collision where both vehicles had momentum to start off with. So let me go through the solution on how I would do this problem. Okay, so to go about solving this problem, I need to give myself a little bit more room up here on the smartboard. So I think a good idea, now that you've interpreted what's going on in the problem, is to write down a statement that shows the law of conservation of momentum. The law of conservation of momentum basically says that the total momentum beforehand is equal to the total momentum afterwards. Now, the total momentum beforehand is the momentum of the F-150 plus the momentum of the Civic, and afterwards the momentum is both of them stuck together. So I'm just going to label that as P prime both. When I read this problem, I find out that I certainly have enough information to find the momentum of the F-150, and I also have enough information to find the momentum of both of them afterwards, but I actually don't have enough information to find the momentum of the Civic ahead of time. In fact, the answer that I'm looking for here, how fast the Honda was going just before the crash, I will find by knowing what the momentum of the Civic is. And so in this particular problem, what I'm going to do is I'm going to solve for the momentum of both of them first, and also the momentum of the F-150, and then I will just subtract those two to find what the momentum of the Civic is. So always a good idea to do a little pre-planning when you're doing this kind of problem. So I'm going to set up a little chart area to where I can do my before and after and keep them separate from each other. Over here, I'm going to find the momentum of the F-150 by taking its mass times its velocity. So that's going to be 2,200 kilograms times 8.2 meters per second. Okay, when I do that on my calculator, I come up with 18,040 Newton seconds. Okay, I know the momentum of the F-150. Remember, I don't know what the momentum of the Civic is, so I'm just going to leave that alone for now. But I do know, I do have enough information to be able to find the momentum of both of them after the collision. Okay, the momentum of both of them after the collision will be their mass times their velocity as they are moving together after the collision. If I take these two masses, 2,200 kilograms, and I add 1,400 kilograms, that's the two vehicles, I find out that their total mass is 3,600 kilograms. And according to the problem, they are moving 15.9 meters per second when they collide. I'm sorry, after the collision. When I multiply those two together on my calculator, I come up with 57,240 Newton seconds. So I now have the numbers that I'm going to need to go about solving this problem. Okay, so remember the statement that I wrote that the momentum of the F-150 plus the momentum of the Civic will be equal to the momentum of both of them. Well, I know the momentum of the F-150 is 18,040 Newton seconds. I don't know what the momentum of the Civic is, but I do know the momentum of both of them is 57,240 Newton seconds. Okay, that means the momentum of the Civic will be equal to 57,240 Newton seconds minus 18,040 Newton seconds. When I do that math on my calculator, I come up with 39,200 Newton seconds. Well, now that I know what the momentum of the Civic is, I can figure out the velocity of the Civic, because the mass of the Civic times the velocity of the Civic will be equal to 39,200 Newton seconds. And the way I find the velocity of the Civic is I simply take the momentum of the Civic and I divide by the mass of the Civic, which is 1,400 kilograms. And when I do that math, I get 28 meters per second. So what that basically tells me is that in this problem, the Ford F-150 that was going 88.2 meters per second was rear-ended by the Honda Civic that was going 28 meters per second. Obviously, the Honda Civic just wasn't paying attention whatsoever. But when that Honda Civic hit the F-150, they hit and stuck together, and they ended up going 15.9 meters per second. That should make a lot of sense. It's like a fast item hitting a slow item, both going in the same direction. When they hit and stick, they should slide together with some speed kind of in between there. So that answer should make perfectly logical sense to you.
This demonstration is meant to simulate the Ford F-150 getting rear-ended by the Honda Civic. So car B will represent the Ford F-150. It's got some masses on top of it to make it a more massive vehicle. Car A doesn't have very much mass at all. What I'm going to do is have car B moving slowly at first, and then have it rear-ended by car A, and you will see that they stick together. When they stick together, they move faster than car B was going, but slower than car A was going. And as I mentioned before, the speed that they will be going really will depend on what the ratio of the masses of the two cars is.
Let's take a moment and have you do one on your own. This example in your notes should be one that you guys could do. I don't want you to put your answer into the clickers. Again, we're not going to try to run the clickers with a substitute, but I still think you should be able to do this problem on your own. So I'm going to give you about 5 minutes to do this, and then I will show you what the solution looks like after you've had some time to work on it. Let's just read it first. A bullet is fired into a stationary block of wood. The speed of the the speed of the .0085 kilogram bullet is 625 meters per second, and the mass of the wood is 2.5 kilograms. Assuming that the bullet lodges in the wood, what is the resulting speed of the wood and the bullet after the collision? So what you should really think about here is that you have one object that's at rest, and it gets struck by another object that has momentum. They hit and stick together, and they both carry the same momentum that the bullet had to begin with. So, like I said, I'll have Mr. Gager pause this for about 5 minutes and give you a time to solve it, and then I will show you what the solution looks like. Okay, so when I set up this problem, I drew a little diagram here to start off with. The purpose of this diagram is really just to help you keep things organized. I have a bullet right here that is firing towards a stationary block, and they end up hitting and sticking together and moving in the direction that the bullet was going. The law of conservation of momentum, of course, is true, that the total momentum beforehand is equal to the total momentum afterwards. Well, the total momentum beforehand really is just due to the bullet, because the block of wood is not even firing at all. So I didn't even account for the block of wood when I did this problem. And I just found the momentum of the bullet ahead of time. The momentum of the bullet is the mass of the bullet times the velocity of the bullet, and I come up with 5.3125 Newton seconds. That really is the total momentum in the system right here, because the bullet is the only thing that's moving. Well, the total momentum is equal to the momentum of both of them as they're stuck together. That means with the total momentum of both of them stuck together, I could really just solve for the velocity of both of them stuck together. When I take the momentum of both times the velocity of both and set it equal to the total momentum in the system, I divide by the mass of both of them. The mass of both of them is 2.5085 kilograms. That's not much bigger than what the block of wood was all by itself. When I do that math, I come up with an answer of 2.1 meters per second. So you have this really fast bullet that hits this stationary block of wood, and the two of them kind of fly off the edge together, not going very fast. And that really is just because the mass of the block of wood was so big as compared to the mass of the bullet. If the mass of the bullet was bigger and still going the same speed, then they would have flown off with a greater velocity. This video clip shows a classic device called a ballistics pendulum, which is basically a way of measuring a block of wood after you shoot it with a bullet. The slow motion video here really shows well how the block of wood moves after the inelastic collision with the bullet. The last kind of interaction that we look at involving the law of conservation of momentum is when they hit and bounce off of each other. So when these objects bounce off of each other, they are called elastic collisions. And the significant difference, of course, now is that although the total momentum in the system is still the same before and after, now you have objects that are separate from each other both before and after the collision. So now you start to get a lot of like velocities where you have VA and VB beforehand, and you have VA and VB afterwards, so VA prime and VB prime. It's really super important that you keep yourself organized when you're doing these kind of problems. That's where the T-chart that I've been showing you, that method will help quite a bit. It also tends to make it to where you have kind of some lengthy solutions that take up a lot of space, but again, that's okay as long as you're keeping yourself organized. You're kind of willing to go with that. So let's go ahead and go through an example of how to do these kind of problems. So in this case, it's kind of fun to have some pictures that are drawn just to help kind of think about what's going on. So this elastic collision example I have shows a semi-truck or a tanker truck moving with a velocity of 18 meters per second, and a car is also going 18 meters per second, but it's going towards the truck. They're going to have some kind of head-on collision, and based on my picture afterwards, it looks like it's going to be elastic. You can see that the front end of the car now is shorter than it was before because it gets smashed up in that process. But we also kind of know that afterwards it's probably going to bounce backwards faster than what the truck is doing, kind of what my picture indicates. So I'm going to go through the solution here to show you how this would work. I like to write out a little statement here at the very beginning to kind of help guide my thinking a little bit. So I'm going to say that before the collision, the total momentum in the system is the momentum of the truck plus the momentum of the car. That's going to equal to the momentum of the truck after the collision plus the momentum of the car after the collision. This statement right here is going to guide my thinking through the rest of this problem. So what I'll do down below here is just calculate what the momentum of the two vehicles are. So first of all, I'll start off here with the truck. The truck has a mass of 3,200 kilograms and a velocity of 18 meters per second. That means that the momentum of the truck beforehand, mass times velocity, is going to be equal to 57,600 Newton seconds. Okay. Now what I'll do is calculate the momentum of the car. The car has a mass of 1,400 kilograms, and it has a velocity of negative 18 meters per second. Okay, so this step right here, guys, I can't underscore how important this step is. The car is going in the other direction from the truck, so you have to make its velocity negative to show that it's going the other way. These two velocities right here, having different signs, show that they're going in different directions, which of course is a very important part of the problem, right? So once I've done that, I say this is negative 18 meters per second. Then I can find the momentum of the car. And when I do that, I come up with negative 25,200 Newton seconds. Okay? So now I have the momentum of the truck and I have the momentum of the car, which are the two pieces of my statements up here. Okay, now what I'm going to do is think about what happens afterwards. So afterwards, I still know enough information about the truck to be able to find it. Its mass is still 3,200 kilograms, and the velocity is now 6.5 meters per second because, I don't know, when it hit the car and slowed down, it actually lost some of its momentum. The momentum of the truck now, mass times velocity, is only 20,800 Newton seconds. The car, of course, I don't know enough information about it to be able to find its momentum because I don't know what the velocity of the car is afterwards. That's the point of this problem. But I'm going to be able to solve that when I look at this statement up here, because now I know the momentum of the truck and the momentum of the car beforehand. I know the momentum of the truck afterwards. Therefore, I'll be able to find the momentum of the car afterwards. So I'm going to rewrite this statement, that statement down here, but I'm going to now have the numbers substituted in. 57,600 Newton seconds plus negative 25,200 Newton seconds. I need to move all that over, equals 20,800 Newton seconds plus the momentum of the car afterwards. Okay, well now I just simply do all the subtraction to find out what the momentum of the car afterwards is. And I come up with a momentum of the car afterwards to be 11,600 Newton seconds. Okay, now that answer makes sense. The car originally had a momentum of negative 25,200 Newton seconds, and now it has a momentum of positive 11,600 Newton seconds. That means the car actually turned around and is now going the other way, which is exactly what happened in this problem. Well, I hope you know what to do from here. I'm going to take the momentum of the car and I'm going to divide by the mass of the car so that I can find the velocity of the car, because remember, mass times velocity is momentum. So the velocity of the car afterwards will be 11,600 Newton seconds, and I will divide by the mass of the car, which was still 1,400 kilograms. When I do that on my calculator, I get 8.285, which basically is 8.3 meters per second. And I need to now define the direction of that final velocity. So I'm going to say 8.3 meters per second in the direction of truck. That's the answer to that problem. This is a very, very, very common elastic collision example. Two objects hit, they bounce off of each other. You basically go through to figure out what was the final velocity of one of the objects. Every now and then you might have to actually go to figure out the initial velocity of one of the objects. But understand that you have, two different objects at two different times. So you really have four sets of variables, and you're going to have to solve around to find one piece of those four sets. Very, very common type of elastic collision problem. There's one more example in the notes that I want you to try to do before you start working on homework problems. So The problem that I want you to work on is example 5 here. It says 2 physics students ride the bumper cars at a carnival. A yellow bumper carrying a hefty physics student is stalled in the traffic lane. A petite physics student in a red car traveling at 2 meters per second rear ends the stalled yellow car. After the collision, the yellow car is moving forward at a velocity of 1.5 meters per second. If the mass of each car is 40 kilograms and the mass of the hefty student is 80 kilograms and the mass of the petite student is 40 kilograms, find the velocity of the red car after the collision. Man, this whole problem is just a big organizational nightmare. So part of what you need to do is figure out how to organize it in the right way, figure out how to label everything well, and then basically find the final velocity of the red car after the collision. Remember, the red car is the one carrying the petite physics student. So I will give you about 5 minutes to solve this. Mr. Gager, again, if you could pause the video long enough for them to try to find this answer, and then I will show you the solution when you are finished. So how did you do? What I did here is I started off by writing this down at the beginning. I always remember in this problem getting mixed up between the red car and the yellow car and the hefty student and the petite student and all of that. I just wrote that down at the beginning just so I could have that to refer to as I did this problem. Then I did my normal law of conservation of momentum statement right here that said that the momentum of the red car plus the momentum of the yellow car beforehand is equal to the momentum of the red car plus the momentum of the yellow car afterwards. And then I went about finding the momentums of all the things that I could. So I was able to find the momentum of the red car. It's 160 Newton seconds, mass times velocity. The yellow car has no momentum because it's just sitting there. The red car afterwards, I don't know what its momentum is. That's what I'm going to have to find out first before I can find the velocity. But I can find the momentum of the yellow car by taking its mass times its velocity. That's 180 Newton seconds. I want to make sure you understand that the direction of velocity of the yellow car is in the same direction as the velocity of the red car. It was just sitting there. It got bumped into. That means it moved forward. Now the question is what happened to the red car in that collision? Well, when I go back now and revisit my momentum statement, I'm able to solve for the momentum of the red car, and it turns out the momentum of the red car is a negative value. Okay, the fact that it has a negative value tells you that the red car actually bounces backwards. And so when you take the momentum of the red car, you divide by its mass, you find out that it's actually slowly going backwards with a velocity of negative 0.25 meters per second. This is a good thing to understand when you do different kind of collision problems, is what some common results are. If you have a large object that is at rest and it gets bumped into by an object that is smaller, the smaller object will actually bounce backwards a little bit. The degree to which it bounces backwards has to do with the ratio of the masses.
Look at these two cars right here. They are meant to simulate the last example that you just saw. I have car A that has no masses on at all, and I have car B that actually has 2 masses on it. So car B is meant to represent the massive, hefty physics student, and car A is meant to represent the petite physics student. So notice what happens when car A runs into car B that is at rest. You can see that clearly car A bounces backwards a little bit, car B moves forwards. Car A really almost has momentum imparted back on it, which is very interesting. The cool thing about it all is that when you look at the total momentum in the system that's due to car A, that is still the same as the total momentum in the system afterwards. It's just carried by both A and B. Okay, everybody, well, that's it as far as the law of conservation of momentum is concerned. I appreciate your patience. I know it's very difficult to learn this way. I spent a lot of time trying to make the videos a little bit more interesting and appealing than maybe just a normal screencast. I hope it worked out for you. I also hope that you were able to get any help that you needed to get. I'll also want to have you do one additional thing, just so I can be sure that you're processing the ideas. The last bit of the video will have I don't know, some questions that I want you to write some answers to as part of your homework, which is going to be finishing up Momentum 2. So when that comes up on the screen, Mr. Gager will just leave it displayed, and you will be able to know what those questions are. So feel free to talk with your neighbors, talk with other people, but I really want you to be thoughtful about how to process these things. So anyway, everyone, I will, I don't know, I'll see you tomorrow or I'll see you the next day. I hope everything went well. Everybody have a good day.